function is continuous at a given point, if you can smoothly, or not smoothly, I guess it doesn't have to be even smooth, if you can draw through that point without picking your pencil up off the paper. So the three examples that are here that lack continuity, and you'll see why, at A, this one is discontinuous at A. The reason for that is because there's a hole there. So if I'm tracing along the curve and I get to that hole, I have to pick my pencil up off the paper, jump over to the other side, and continue drawing the curve. So for that reason, we would say it's discontinuous at A. Let me ask you this about part A. What if this was 5, we'll say. And on this one, I'm going to make this 5 and this 10 for when we get there. And on this one, I'm going to make this 10 and this 13. So we can talk about a couple things that are going to start to become more important. If I looked at A and I said, what is f of A? What is the function value at A? What would you tell me? So there's a point at A comma 5. It doesn't exist. Maddie's correct. It doesn't exist. There's no point there. There's a hole there, which means the function does not exist there. So f of A does not exist. What I also will ask you about A is what is the limit, though, of this graph as we approach A? As I approach A from the left and I approach A from the right, am I pointing at each other? Yes, and at what value is that? 5. So the limit as we approach A is 5, but the function value at A does not exist. Okay? And those are going to be two important things to evaluate when we don't have a picture in front of us to look at, to review continuity. So when we look at the picture, we just realize we have to pick our pencil up off the paper and go to the other side to continue this. So it's discontinuous at A because there's a hole there. So a hole is one reason for discontinuity. On B, if I'm tracing this graph left to right, can I get all the way through point A without picking my pencil up off the paper? No. I get up to A, coming from the left, and then it jumps. So I have to pick my pencil up off the paper, so this discontinuity is caused by a jump. Now, to evaluate those same two things here, and I gave you numbers already, what is f of A on this one? Where is the point? A comma what? 5. How about the limit as x approaches A? If I approach A from the left and I approach A from the right, are my fingers pointing at each other? No, therefore the limit does not exist. So in the first two examples, you can see the function value doesn't exist, but the limit does in the first one. And on the second one, the function value exists, but the limit does not. Both justify discontinuities. Okay? And then in C, can I trace along this continuously without picking my pencil up off the paper? No, I can't. There's a hole there again. So this is another hole. So it is discontinuous at A. We're going to call it a hole because it's the same. But what is going to be different about this is that what is f of A? 13. And the limit as x approaches A? 10. So we have three cases here. Function value doesn't exist, limit does. Function value exists, limit does not, or they both exist, but they're not equal. By definition, the only way something can be continuous is if the function value exists, the limit exists, and they're equal to each other. Do you follow? And that's what this definition is right here. A function is continuous at A when the limit exists, the function value exists, and most importantly, they're equal to each other. Faith. Well, in both cases, when there's a hole involved, the limit will exist based on where the hole is. So this one's hole I put at 5, and this one's hole was at 10. So the limit existed for both of those holes. One was at 5, one was at 10. The only difference between these graphs is that this one's function value did not exist. There was no other removed point. And this one had this other weird removed point up there. Okay? So when we jump into these examples, and this first one is rational, we're going to review probably first trying to wrap our head around what this graph looks like. For rational graphs, you always want to factor first and cancel. Because if you have a cancellation, you're going to have a what? Good. So on this first one, I'm going to just up here factor my denominator. 2x and x, 1 and 1, minus and plus. So I do have a hole, and where is my hole? -1/2. If you want to figure out the location of your hole, you've got to tee up essentially the factor that canceled. 2x plus 1. When you tee that up and set it equal to 0, you get -1/2. So we have a discontinuity, therefore, at -1/2. And so this then simplifies, with the exception of that hole. This graph, the original graph, is going to look just like this graph. What other features could you tell me about this graph? The fact that we still have an x minus 1 in the denominator tells us what? What's happening at 1? Nope. Do that hand gesture again, Maya. She's this. This would be known as a vertical asymptote. Okay? This. Very good. That's what you meant, right? So we have a vertical asymptote at 1, which anytime you approach a vertical asymptote, you have to pick your pencil up off the paper and jump to the other side. So this graph, just so we have a visual in front of us, has a vertical asymptote at 1. How about your horizontal asymptote? What's the rule here? Small over big, big over small, or same over same? Small over big, which means your horizontal asymptote's at 0. That's not going to affect our continuity so much, but it's just going to give us a better image. You guys love your rational graphs. What did you say? No, because again, you would tee up the denominator. Where is this undefined? If this fraction is going to be undefined when x is 1. Okay. And so your graph, like rational graphs do, this is like the parent graph of a rational. I just shifted right 1. So when we're sitting here determining whether or not this is continuous at 2, now we can look at the graph. If this vertical asymptote's at 1, oh wait, we have a hole too. Where's our hole? -1/2. So that would be right around there somewhere. Put an open hole on the graph. So is this continuous at 2, which would be over here somewhere? Can I draw through this point without picking my pencil up off the paper? Yes. So is this continuous at 2? Yes. Is it continuous at 1? No. What's that? Yes. You have to, let's just, again, it's jumping back a few chapters, rational graphs. They were never our favorite. We saw them again recently with what? What did we just do our horizontal asymptote rules with? Oh, limits as we approached infinity. But I didn't make you draw those whole graphs all over again. But the main things we care about on these rational graphs are your vertical asymptotes, your holes, and your horizontal asymptotes. vertical asymptotes come from the denominator after simplification. Your whole comes from anything that cancels. And your horizontal asymptotes come from your rules. Big over small, small over big. Okie doke. On 2, JR, factor the denominator first for me. Okay, then does this simplify or no? To what? Okay, so you've got 3 questions to ask. Do we have any vertical asymptotes? Do we have any holes? And do we have any horizontal asymptotes? And if so, where are they? So, do we have a vertical asymptote? And if so, where is it? Okay, your vertical asymptote comes from any zeros in the denominator. At the very end of the problem, though. -2. So x equals -2 is a vertical asymptote. Holes. Do we have any holes? If something canceled, you had a hole. At 2. Good. And horizontal asymptote, you look at your original, back to the beginning. Based on your small over big, big over small, same over same. Which is where? 0. Okay, so if we sketch this, horizontal asymptote at -2, horizontal asymptote at 0, and then this is just the parent graph. Now the parent graph of a rational is in the first and third quadrants. This has just been shifted left 2, and your asymptotes kind of give you a new first and third quadrant. So like this, and like this. And then you can insert your hole at approximately 2, which would be somewhere over there. So is this continuous at 1? What do you think, Brock? Okay. Where's 1 on your graph? Let me see where you're pointing. Right. So is it jumping over 1? Is there a hole at 1? Is there an asymptote at 1? What is at 1 that is making it discontinuous at 1? Because he pointed here. So is there a hole at 1? Okay. Is it jumping at 1? Is there a vertical asymptote at 1? Okay, then it's continuous at 1. So that would be a yes. It is continuous there. Because I can't go much past 1, but I can at least trace before and after 1. Doesn't matter how short that stretch is, as long as you can trace through there without jumping over it. It's going to be a hole, an asymptote, or a jump that's going to make it discontinuous there. And if you don't have any of those, then you're good to go. At 2, we have a hole. So this is a no. Any questions? So if I were going back up to the top, I would probably add a third graph, just a third scenario that shows something with an asymptote at A. Because that's really the third and final reason. Hole, jump, or asymptote. So a couple things happen at A. Number 1, if there's an asymptote there, what's f of A? What'd you say, Maya? Does not exist. Good. And then your limit as you approach A, if I'm approaching A from the left and I'm approaching A from the right, are my 2 fingers pointing at each other? No. So the limit doesn't exist either. And by the way, does not exist equaling does not exist is not a thing, right? That's not true. 2 does not exist don't equal each other. That makes sense? They actually have to both exist and match. Correct. Well, I'm just telling you in case you ever see, you're like, why? DNE equals DNE makes sense to me. That's not the way it works, okay? Has to be 7 equals 7 or something of that nature. Good? Okay. That's it. All right, I'm going to pass you 3 things. Homework for tonight, limits quiz, and your quarterly. Okay?